Hello, everyone. Good afternoon.
Good afternoon.
Good afternoon. So today we're going to start the second part of the course out of 3. As I mentioned from the beginning, what we've done so far has been basically a collection of fundamental examples, because dynamical systems is really built on these examples. However, as you have seen, there is basically an unlimited number of examples, so we cannot just study all the examples one at a time and just take one more and try to understand it, take one more to understand it. We need to have a little bit more systematic approach and try to understand which examples are similar to other examples. So this part 2 of the course is really introducing the notion of the classification. Of dynamical systems. So the first thing we want to understand is what we mean by classification. Have you seen this concept in some other, is there some problem? There's only Junaid, Ruba, and Ling. Hello there. Okay, others are joining. So, do you know of other areas of dynamical systems where you can recognize this notion of classifying mathematical objects? What other mathematical objects, what other areas in mathematics is there some kind of classification so that we can have some idea of what this means? Do you have some?
Surfaces.
Excuse me?
Surface.
Surface. So what do you mean by surface?
Classification using Gaussian curvature.
Is that a classification? What do you mean by classification using Gaussian curvature? You mean surfaces of positive curvature, of negative curvature? Is this what you mean?
Yeah.
Yes, very good. So this is one way in which you can start creating some categories, right? But on the other hand, we want to go a little bit deeper, right? So what is it in the case of surfaces, what is it that they all have in common?
Isometric.
What do you mean by isometry?
Preserves the length after the distortion.
Ling, you need to say some full sentences here, not just keywords, right? So I guess what I'm trying to say is that we need some kind of notion of equivalence, right? When are two objects the same? Right? So it's a little bit more rigid than just making some broad categories, right? So we've already seen some broad categories. For example, I said we have 0-dimensional dynamical systems, 1-dimensional systems, 2-dimensional systems. These are general categories. Or we can have homeomorphisms, or we can have full branch maps. These are general categories. But what does it mean to say that two dynamical systems are different? Or what does it mean to say that two dynamical systems are the same? Right? For example, so question, if we take f of x equals 1/2 x right? And g of x equals 1/3 of x. Are these the same? Are they somehow, in some way, is there some way that we can talk about being the same? Or suppose we take f of x equals 2x mod 1, or g of x equals 3x mod 1. Or, for example, let's take f of x equals x plus b mod 1, or g of x equals x plus b tilde mod 1, you know, two different b's. So they're all of the same kind. This one is of the same kind, this one is of the same kind, this one of the same kind. So what does it mean to say that two dynamical systems are the same? What other objects in mathematics? For example, if you think about metric spaces or topological spaces, is there a notion of what it means for two topological spaces to be the same?
Homeomorphism.
Homeomorphism. Exactly. Right? So when you have a homeomorphism between topological spaces defines an equivalence relation in the space of all topological spaces. Right? So it really defines, of course, the fact that two topological spaces are homeomorphic does not mean that they are the same, but it means that they have certain characteristics in common. Right? And in topology, homeomorphism is the fundamental property of equivalence, because the fundamental topological characteristics of a topological space, like compactness, connectedness, are preserved by homeomorphisms. Right? So homeomorphism is a good equivalence relation in the world of topological spaces. You also have equivalence relations in the world of group theory, for example. I don't know if you have done some group theory, right? But you can talk about two groups being isomorphic, for example, right? So in many areas of mathematics, in most areas of mathematics, really going from algebraic geometry to topology to dynamical systems, one of the fundamental problems is to define some good equivalence relation in the space of all your topological spaces, or all your groups, or all your whatever the objects that you're
Morphisms in the category theory, in the terms of category theory, morphisms and
I guess so. I guess so. That's the basic idea, right? The abstract idea is that you want to define something that is going to tell you that these two systems, these two objects are the same up to some property, right? Sometimes you can have various, as we shall see, we can have various equivalence relationships that preserve some characteristics and not other characteristics. So the purpose of these next few lectures, well, the purpose of today is to give some kind of natural way to define some equivalence relation in the space of all dynamical systems, right? And to see what kind of properties this equivalence relation satisfies, right? Because that will allow us then to say, okay, if we can prove that one dynamical system in your equivalence class has certain properties, and we know that these properties are preserved by the equivalence relation, then automatically you conclude that all the systems that are equivalent to that one have these properties. So there are several different interesting equivalence relations in dynamical systems. So let's first of all think together a little bit about what we expect from an equivalence relation. So intuitively, in an abstract setting, suppose we have two dynamical systems. We have a map F from X to X. and we have a map G from Y to Y. So here you take some initial condition x0 and you map it by f, right? This is f of x1, this is x2, f of x naught, and so on, right? And then here you take some point y0 and you map it by G. So I look at these two systems, right? And I would like to have some criteria that will tell me, well, these are more or less the same system in some sense. So what would I like this notion of equivalence to preserve? If I tell you these two systems are the same, and then I tell you, okay, this system has a fixed point, would you expect that this other system should also have a fixed point? If I tell you that the systems are the same? Or would you be surprised if I say, yeah, they're the same, but this one has a fixed point, but this one does not have a fixed point, but still they're the same in some way? What kind of properties should an equivalence preserve in the two systems? What do you think, Junaid?
Somehow the orbits should be similar.
The orbits should be similar. That is a absolutely very good observation, because if you remember right from the very first class, the orbit is the fundamental object that we're interested in a dynamical system, right? It is the very first concept that I defined when you have a map, and the very first thing that I do here, when you have a map, from a dynamical system point of view, what we're interested is in the orbits, right? So that's exactly right. So the orbits should somehow be similar. So, Ruba, are you there?
Yeah.
What do you think? What do we mean by saying that the orbits should be the same in these two systems? So, or there should be somehow the orbits, they should have the same orbits in some way, right? These are two different systems defined on different sets. How can we match up the orbits?
Is by linear conjugation.
Excuse me?
Is it by linear conjugation between the two maps?
Sorry, the audio again is not very good. By what condition?
Linear conjugation between the two maps.
Conjugation, you said?
Yeah.
Right. So this is what we're trying to work towards, right?
Yeah.
We're trying to work towards that. So I would say that the first condition we clearly would want is that, for example, if f has a certain number of fixed points, G should have also the same number of fixed points, right? Because following this general concept that Junaid said, that the orbits should be the same, the simplest way to say that, first of all, is at least the fixed points, you should have the same number of fixed points, right? Again, the simplest kind of orbit is a fixed point. So if you have 5 fixed points here, and this one has 4 fixed points, then something is missing, right? It would be surprising to say that these are equivalent if they have different number of fixed points. And the same for periodic points, right? So if you have a periodic point here of period 7, you would expect that you would find a periodic point here of period 7. So you want some kind of matching up all the fixed and periodic points should be the same in the two systems. And what about non-periodic points? So how can we match up orbits? So, well, certainly we have to map points to points, right? So we want some kind of bijection, right? If we want these two dynamical systems to be the same and we want to match up all the orbits, then we want some kind of bijection between the points of x and the points of y, right? So x is a bijection. And then we want this bijection to match up all the fixed points. So if it any fixed points here, it will match them up one to one. If it has periodic points, it will match them up, right? And then if we have an orbit that is not periodic, then suppose that x0 maps to y0. Then how do we make sure what we really want is H to map all the points in the orbit of x0 to the points in the orbit of y0. Right? That's what it means to match up all the orbits. So I take this bijection x between these two spaces and I say, okay, if H maps x0 to y0, then I want H to map x1 to y1, x2 to y2, x3 to y3. So the question is, can I do that? So how do I define this? So I have this definition, is that H from x to y, so wait, let me write it slightly differently. So F from x to x and G from y to y are conjugate, as Luba said, if there exists a bijection H from x to y such that, so what do we want this bijection to do? So if H map x0 to y0, so we take H so what we want here is that if H, let's write it down here, so if H of x0 equals y0, right? Then what we want is that H of y1 would be, sorry, H of x1 should be y1, right? So x1 is just f of x0, and y1 is just f of y0, which is H of x0. So the formal way to put everything here together is saying that if you compose H with f, H composed with f, which means that if you take a point here, x0, and you apply f, and then you apply H, you get y1. And this gives you exactly the same point that you get if you apply H to the initial point and then you apply G, right? So H composed with F is the same thing as G composed with H. Okay, so what this means, just as an example, i.e., or this is exactly the same, so this means that H applied in f of x is equal to G applied in H of x, right? So if you choose any point here and you apply f and then you apply H, that's the same thing as applying H and then applying G. Okay, this is the conjugacy condition. This is a very important condition. And notice, of course, that this is preserved, right? Because the same thing will happen when you iterate again. So if this implies, okay, this is easy to check. Notice that then this implies that H composed with Fn is also equal to Gn composed with H. You can easily check that this is the case. So if you have this conjugacy condition, then it means that also H will map x2 to y2, H will map x3 to y3. So H will map all the points of the orbit of x naught. If H maps x naught to y naught, then it must, and it satisfies that condition, then it must map all the points of the orbit of x naught exactly to the corresponding points of the orbits of y naught. So H is called a conjugacy between the dynamical systems F and G, and it does exactly what Junai said, which is it matches up all the orbits, right? Exactly. So every orbit that you have here, you have a corresponding orbit here, right? And it's easy to check that this must map fixed points to fixed points, periodic points to periodic points, because it must send all the orbits to themselves. Any questions? Okay, so what are the other things that we're interested in dynamical systems? So this conjugacy maps orbits to orbits, but how do we describe, in the examples we've looked at, we have sometimes looked at certain properties of orbits, right? So in the case in which the orbits are not periodic, we describe the omega limit set of an orbit, right? And so it would make sense to take this one step further and say, okay, maybe we want a little bit more. Maybe to say that two dynamical systems are the same, we would like also that if here we have the omega limit set of x naught, okay, so if you look at this orbit, for example, it converges to some point P, or it converges to some set, or maybe this orbit is dense, then we would like the same thing. We would like this H also to map the omega limit set to the omega limit set. If it maps x naught to y naught, then we would like it also to make sure that it preserves. So for example, if you have one system in which this orbit converges to a fixed point, right? Then you want also this orbit to converge to a fixed point, and you want the two fixed points to be the correct fixed points, right? So H maps all the fixed points to the fixed points, but we don't know if it maps exactly the fixed point that is the omega limit set of 0 to exactly the same fixed point that is the omega limit set of y is 0, right? Because suppose you have 5 fixed points, then according to this definition, it doesn't really matter as long as H maps fixed point to fixed points, it doesn't matter which fixed points it maps to which fixed points. So you've got your 5 fixed points, and it doesn't matter which one, you can change it around, right? And if you have this conjugacy, you can decide to change. This is not unique, this conjugacy, right? Because it's just a bijection that maps orbits to orbits. So if you have 5 fixed points here, and this maps them to 5 fixed points there, and I decide, no, sorry, I didn't want that. I want to map this fixed point to a different fixed point, it will still satisfy exactly that definition. Is that okay?
We don't require it to be continuous.
Sorry, Luba, I don't know why the sound is so bad. I don't think it's just my ears.
My probably is very bad. But I'm asking about the continuity.
Yes, exactly, Luba. Very good point. So the question is whether if this bijection had some kind of continuity properties, then we could resolve this problem, right? Because if you had this orbit here converging to some omega limit, and then you would like to make sure that this H is mapping these points of this orbit, and this orbit is converging to that, so it would kind of make sense that that's how you choose H, to preserve that kind of limit points, right? It's exactly right. So, so how can we change that? Well, we could change this from being a bijection to being a homeomorphism. Which is a stronger condition. And then we could call this, and then we call this, we say that this is topologically conjugate. And then we will see how in the exercises you can see that in this particular case, if this, of course you need a bit more structure here, right? So the first definition of conjugacy did not make any assumption on X and Y. They're just sets, which is exactly how we were defining right from the beginning. To define a dynamical system, you do not need any structure, but to define omega limit, you need to have a topology. So we generally assume X and Y are metric spaces, but if you have a topology, you can define the omega limit. And so if these two are metric spaces or topological spaces, we can define a homeomorphism, and this property here is exactly the same. It maps orbits to orbits, but in this case, it's possible to prove that it must map the omega limit set of X naught to the omega limit set of Y naught if H maps X naught to Y naught. So it also preserves omega limits. So this is a stronger condition. So one thing that I forgot to mention is to show that this is an equivalence relation. Why is this an equivalence relation? On the space of dynamical systems. If you remember the properties of equivalence relations, okay, you can easily check. So if F is equivalent to G and G is equivalent to some other system, then F will be equivalent to that system, because you can just compose the homeomorphism. I will leave that also as an exercise, but it's very easy to check that conjugacy is an equivalence relation in the space of all dynamical systems. Topological conjugacy is also an equivalence relation in the space of dynamical systems, right? Notice that topological conjugacy implies that two dynamical systems can be topological conjugate only if the spaces themselves are topologically equivalent, right? Because the fact that you have a homeomorphism, as we said before, is the notion of equivalence between two dynamical systems, which makes sense, right? So you can never have, if you have a dynamical systems defined on the interval and one defined on the circle, these two can never be topologically conjugate because the interval and the circle are not homeomorphic, so you will never be able to have that independently of the dynamical condition. So in some sense, this includes two conditions. One on the space is a necessary condition, and then once the space are homomorphic, you need to satisfy this condition between the maps. Can we go even stronger than homeomorphisms? Can we define an even stronger equivalence relation?
Differemorphism.
That's right. That's right. So we could also further strengthen this and say, well, that's not good enough for me, right? Because homeomorphism is good. Okay, it preserves omega limits. But actually, I would like this condition, I would like this to be, for example, a C1 differemorphism, right? And in this case, I'm going to call this a C1 conjugate. So topological conjugacy is sometimes called C0 conjugacy also because C0 is continuous. A C1 conjugate, and you can also define C2 conjugate, C3 conjugate, analytic, real analytic conjugacy, C infinity conjugacy, right? So the word conjugacy, so there is a kind of Lipschitz conjugacy, right? So really the quality of the conjugate refers exactly to the regularity of the conjugacy, refers to the regularity of the map which we use to conjugate the two dynamical systems. And as we shall see, in different situations, there are many reasons to choose one or the other. Okay, but I will have a little discussion now about which one we are interested in. So, of course, if you have a C1 diffeomorphism, then it means that these spaces must be more regular than just metric space, right? They must be spaces in which it makes sense to define a C1 diffeomorphism. So they have to be, for example, Rn or the circle or the interval. They need to have some spaces with a differentiable structure, right? Like the interval, for example. So let's suppose, so which additional structure do you think that this preserves? If we take two interval maps, right? Suppose we take F, I to I, and G, J to J. Suppose I and J are intervals, so that we can define a C1 conjugacy. So notice, first of all, that of course a C1 conjugacy is in particular a topological conjugacy, right? And a topological conjugacy is in particular a conjugacy, right? So these ones are stronger. One is stronger than the other. So if you have a, if F and G, suppose F and G are C1 conjugate, what additional properties of F and G do you think that this C1 conjugacy implies, as well as the properties of C0 conjugacy? So let's, for example, let's look at a particular example that we have discussed, for example, interval diffeomorphism, right? So let's suppose that we have here an interval two interval diffeomorphism. This is F, and then we have an interval diffeomorphism, which is G. And let's suppose, right, so we remember we said the interval diffeomorphism looks something like this. So if I tell you that H is C0 conjugacy, so that there's a homeomorphism, right? Then what can you tell me about the graph of G? We know that G must have the same number of fixed points. So it must have 1, 2, 3, 4 fixed points. And it must send omega limits to omega limits, right? So in this case, we have some of these fixed points are attracting, some are repelling, right? If you remember, so here we have this fixed point is attracting, because if you take an initial condition here, it will converge to this. If you take an initial condition here, it will converge to this. This fixed point is repelling, this is attracting. So I need a homeomorphism that will map I to J. And this homeomorphism must map fixed points to fixed points, so there must be 4 fixed points, and it must map attracting fixed points, because the image under H of this point must converge to the corresponding fixed point here, right? So basically, it would look more or less like this in the same way, but it could be in a different position, right? So they could be like this, then this point could be here, then maybe this point could be here. So perhaps these are topologically conjugate. At the moment, we're not proving that. In fact, in the next class, we're going to develop some techniques to actually prove. We're going to state a theorem that tells us when two interval diffeomorphisms are topologically conjugates or C1 conjugate, okay? But at least we know that these two pictures are consistent with topological conjugacy. Now the question is, are they consistent with it being a C1 conjugacy? What additional properties does a C1 conjugacy need to preserve? Do you think? I'm not expecting that you necessarily know the answer, but let's think about it a little bit. What if this conjugacy is differentiable, is C1? What difference does it make? Maybe it's the same as topological conjugacy. We don't gain anything by knowing that the C1 conjugate.
The inverse?
What about the inverse?
Inverse of F and G. Yeah.
So conjugacy is a kind of a symmetric relationship in all these cases, right? So in all cases, H is always invertible because H is always a bijection, right? If it's a homeomorphism, then it's invertible. If it's a C1 diffeomorphism, it's also invertible. So that's a good point. But we always have H. I put this arrow here, but it's always really invertible. So let's explore this a little bit. Maybe it's not that easy to actually arrive at the solution, but let me say that maybe the derivative, if it's C1 conjugate, maybe it should also say that there is some relation between the derivatives of these two, right? Because after all, the C1 conjugacy is somehow, if it's going to be any stronger than the topological conjugacy, it somehow has to do with the fact that it's being C1, right? So maybe it's telling us some relation between the derivatives of F and the derivative of G, right? And in fact, what it does Okay, so maybe I will not do the calculation. I will leave it as an exercise. But the interesting statement is that lemma is that if f and g are C1 conjugate, in this one-dimensional setting, conjugate interval diffeomorphisms, and so H then, how do I want to say? So if H, let P in I and Q in J be fixed points such that H of P equals Q, right? So suppose H maps this fixed point to this fixed point, right? So this is a point P, and H is a point Q. So suppose H maps this fixed point. So H is a C1 diffeomorphism. So H is going to map these endpoints to the endpoints and is going to map each of these fixed points to the corresponding fixed point, right? So H, there's nothing strange about H, right? Just the fact that it's a homeomorphism already gives you a lot of clues that it must just map this in such a way that all the fixed points match. But what we have is that then the derivative of f at P is actually equal to the derivative of G at Q. So it means that these derivatives have to be the same at these points. So if you think about it, this is a much, much stronger notion of equivalence, right? Because it's saying not only do you need to have the same number of fixed points for them to be C1 conjugate, but at each fixed point, you must have exactly the same derivative. It does not mean that the derivative, as you shall see as you do the exercise and as you think about this, it does not mean that the derivative should be the same at every point. No, the two maps can be C1 conjugate and the derivative can be different, but if you have a fixed point, if you have fixed points that map to each other, the derivative must be the same. If you have periodic orbits, then the derivative must also be the same at the periodic orbit. So a C1 conjugacy is a very strong conjugacy, right? It's this, I wanted to give these examples because I wanted to emphasize the flexibility that we have in choosing the fact that you can choose different levels of notions of equivalence depending on how much of the structure you want to be preserved. And for different reasons, you may be interested in different notions of equivalence. In general, just the initial conjugacy, where you just have a bijection, is an extremely weak form of equivalence. As I said before, it may, for example, it maps the set of fixed points to the other set of fixed points in a random way. So you might have an attracting fixed point mapping to a repelling fixed point, right? Even though everything still matches up in this way. So usually, if you just say that two systems are conjugate, it's not a very satisfactory definition of conjugacy. It is formally correct, but it doesn't match up to what we expect. Really, we expect from an equivalence between two dynamical systems. If you have a topological conjugacy, it already makes much more sense because if you have an attracting fixed point, it means the nearby points converge to that, and then this topological conjugacy must map attracting fixed points to attracting fixed points. If we have a C1 conjugacy, it is saying much, much more. It is saying not only it maps attracting fixed points to attracting fixed points, but these two fixed points must have exactly the same derivative. Right? So as we shall see, that is a little bit too strong a form, because it says, okay, you know, if I just change just a tiny little bit the derivative there, I don't even change the position of the fixed point, I don't change anything, I change this a little bit, and then it will no longer be conjugate to that map there. Okay? So in some cases, it is interesting to know what the two systems are C1 conjugate, but it is an extremely strong form of conjugacy.
The last lemma is not just true in the interval maps, right?
Can you say that again, Ruba? You said it's true in infinite what maps?
No, I'm saying it's not just true for interval maps, right? It is true in general.
Oh, yes, thank you. For interval maps, so you mean this lemma here?
Yeah.
Yes, so what you get in higher dimensions is that you have the same eigenvalues for the derivative. You have, wait, I need to remember. So if you have two fixed points in higher dimensions, I think this will imply that they should have the same eigenvalue. The two, in that case, the derivatives are linear maps, and you do not have, you know, it does not really make sense to say that these two maps are the same. They're not the same, but they have the same eigenvalues. Yes. Thank you. That's an important point, yes. So it's even in higher dimensions, it tells you that the derivatives at the two fixed points are related in some way, right? Not that they're exactly the same, but they have the same eigenvalues. As we shall see, there's also a question about how, when are two linear maps equivalent? We're going to think about that. Okay, so before we have a break, let me give one example, an interesting example of two systems that are conjugate. I'm going to write down the following two maps. So example. So I'm going to define a map F from -2, 2 to -2, 2. Which is going to be f of x equals x squared minus 2. And the graph of this map, basically, well, the graph of this map, this is -2, 2 from -2, 2 to -2, 2. And if you think about this map, it's quite easy to see that it looks like this. This is just a quadratic map shifted down. And then I'm going to define a map G from 0, 1, 0, 1. And this is easier to actually draw the picture, but I will also write down the formula. So this is 1/2, 0, 1, 1/2, 1. And this map is going to be this map here. So this is just g of x is equal to 2x if x is between 0 and 1/2, and 2 minus 2x if x is between 1/2 and 1. So I put the closed intervals on both sides because it doesn't really matter. So these are both full branch maps, right? In the sense that they have full branch with 2 branches. So we have not yet really studied the dynamics of either one of these. This one is piecewise affine. Remember, right? Piecewise affine full branch maps, because here the derivative is constant on each branch. This one is just differentiable piecewise maps, C infinity even, or C1, C2, on these 2 branches, but the derivative is not constant. In fact, the derivative is 0 here, and that has actually a big impact on the dynamics in general. And it turns out that these 2 maps are conjugate, and surprisingly so. And in this particular case, we have a very explicit conjugacy. So in this case, we can define the map H from 0, 1 to minus 2, 2. Where H of Z is equal to 2 cosine pi Z. So what does this map look like? Let's just make sure that it works. So this is a map from 0, 1 to minus 2, 2. So let me draw it maybe like this. This is 0, 1. Here is minus 2 plus 2. Okay, so what does this map look like? Well, so this is just a cosine, right? This is just cosine pi. So here the period, so as z goes from 0 to 1, this goes from cosine 0 to cosine pi, right? So, and then the amplitude is 2. The amplitude of the oscillation is 2. So this is a very simple. This is just, so the cosine of 0 is 1. The cosine of 0 is 1 multiplied by 2 is 2. So this map is 2 here, right? And then it, when z is equal to 1, this is like cosine pi, which is minus 1 times 2 is minus 2, so it's minus 2. In the middle, you have z equals 1/2, which is cosine pi over 2, which is 0. So this is really just a piece of a cosine curve like this, which is stretched. Like this, right? And so this means this is a map that maps this interval 0, 1 to this interval 0, 2. It maps the point 0 to the point 2, right? So it's orientation reversing, right? It's going, this is a, so what is the regularity of this map? This is a bijection, right? So, wait, so first let me write, so lemma is that H is a conjugacy, so we have that F composed with H equals H composed with G, and I will leave this as an exercise. It's a simple exercise because this is very explicit. You literally, we have the formulas for all of these, okay? So you can check that it is a conjugacy. Okay, I will leave the proof as an exercise. And what kind of conjugacy is it? What is the regularity of this conjugacy? Besides being a bijection, is it a homeomorphism? Is it a diffeomorphism? What is H?
It's just continuous and
H is continuous. Is it invertible?
yeah.
Yeah, it's just the cosine. Cosine, right? So it's the cosine on this interval. So is it a homeomorphism?
Yeah.
Is it a diffeomorphism? It's almost a diffeomorphism, right? Because why is it not a diffeomorphism? Can anyone see? Why does it fail to be a diffeomorphism between these two intervals?
Derivative vanishes somewhere.
Exactly, where? Somewhere where? Somewhere here, right?
It's the following problem. Sinus pi z and 0 and 1. Sinus pi z equals to 0. If z equals to 0, boundaries.
At the boundaries, right? Exactly, Milmokshin. So this is the cosine. This is a piece of the cycle of the cosine curve. The derivative is 0 here. So why does the 0 derivative, why is that an obstruction to it being a diffeomorphism? What's the problem with having 0 derivative? It's still a bijection. It's a homeomorphism. It's differentiable everywhere. It's C1. Why is it not a C1 diffeomorphism?
So inverse is not differentiable.
Exactly, right? Because the inverse would have infinite derivative here at these endpoints, right? The inverse is differentiable everywhere except at the endpoints, because if you have a diffeomorphism, you need the inverse to be also a C1 map, and a C1 map means the derivative should be finite, right? When the derivative is infinite, it is not classified as being C1. So this is actually a C1 diffeomorphism on the open intervals. If we took this on the open intervals, it would be a C1 diffeomorphism. Okay, so if we could actually define these dynamical systems if we wanted to. We could try to define, well, it's a bit tricky to define them on the open intervals, because then this point here would map, this point maps to the end point, which would not be included. But so it needs to be defined on the closed intervals. So these two systems are topologically conjugate. They're not C1 conjugate, although, again, I will give this in the exercises, although you see that this proof still applies, even though they're not C1 conjugate, the conjugacy is C1, right? So it does not apply at the endpoint. So if you notice, the derivative at the endpoints is not the same. This is also why it cannot be C1 conjugate, right? Because here we have a fixed point. Which point is this fixed point mapped to under the conjugacy? Here. Here you have two fixed points. Here also you have two fixed points. One is here and one is here. These are two fixed points where the graph intersects the diagonal. So clearly, this fixed point on the end, on the boundary, is mapped to this endpoint, right? And this fixed point in the interior is mapped to this fixed point. And you can check, because we know what the derivative at this fixed point here, this derivative is 2, because the derivative everywhere here is 2, here minus 2, the derivative here is minus 2. You can check, I don't think the derivative here is minus 2. I'm not sure, you'd have to calculate, but you can easily compute exactly the fixed point, and I don't think it's 2. But certainly here it's not. The derivative here is 4. If I'm not mistaken, the derivative is 2, so it cannot be C1 conjugate. But as we shall see, so I want to give this as an example because it's an example where you can compute the conjugacy very explicitly. We have an explicit formula. And although we have not studied this before, we will study in the next couple of weeks the fact that this is a full branch piecewise affine maps is much easier to study than these maps that is not piecewise affine, right? In particular, it will be easy for us to show that for the piecewise affine map, we have, for example, a lot of periodic points, just like in 2x mod 1. Right? It turns out this is very similar to 2x mod 1. Instead of having the two branches having the same orientation, one branch is orientation preserving, the other one is orientation reversing. But it turns out that a lot of the dynamics is the same. In particular, you have a dense set of periodic orbits for this. We will show that, okay? And it is much more difficult to show it directly for this because it's not piecewise affine and it has zero derivative. But using the conjugacy, you can deduce that, right? So the fact now that we've shown directly that these systems are conjugate, which means that certain properties of the dynamics of this map also hold in this map. So the problem of conjugacy and of classification is not just a kind of formal one because we want to have some classification. It can really help. This is what we're going to show also in some examples, because sometimes it's easier to prove things about one map, and then these imply the same thing for all the other maps. So the fact that this has a dense set of periodic orbits, the density of a set is preserved by homeomorphisms, right? And all the periodic orbits here are mapped to periodic orbits here, which means that we conclude that periodic orbits are dense also for this map here, okay? And then also we know what the derivative is for periodic orbits here, right? Because the derivative is always just multiples of 2. The derivative is always either 2 or minus 2. So if you have a periodic orbit of period 5, then the derivative of the fifth iterative map of the periodic orbit will be just the absolute value of the derivative will be 2 to the power 5. Okay, this will always be the case for every periodic orbit has, at the end of the periodic orbit, period 2 to the k. The absolute value of the derivative is 2 to the k. This is not at all obvious here, okay? But this implies this. In this case, if you have a periodic orbit of period 5 and you have a dense set of periodic orbits, you have lots, then this periodic orbit will have different derivatives, right? Here it will have big derivative, here it will have small derivative. But if you look at a periodic orbit of period 5 and you take the product of the derivatives, it will come to exactly 2 to the power 5. And we know this because it's topologically conjugate to that. And even though it's not C1 conjugate, it is still C1 everywhere except for the endpoints, so you can still prove that lemma and still show that you get this property, right? So this lemma does not really need necessarily the two maps to be C1 conjugate, but in this case in which this map, the conjugacy is C1 except at the endpoints, then you can still do the same calculation, but you just cannot do it at the endpoints, and the endpoints is only place where you have fixed points which do not have the same derivative. Okay, so let's just take a 4-minute break, okay, just a quick break, and then come back because I want to finish, tell you where we're going from here. Okay? Get a glass of water. See you in a minute, in 4 minutes. So now we have defined several notions of equivalence of dynamical systems. I've kind of argued informally that topological conjugacy is the most balanced in some ways. So we are mostly going to focus on that. Usually, unless I specify, we will talk about two systems being conjugate when they're topologically conjugate, right? Because just normal conjugacy is too weak. C1 conjugacy is very strong, but it's good to keep in mind this difference. So this notion that two systems are equivalent gives rise to the possibility of asking some extremely interesting questions, right? Because now we have an equivalence relation on the space of all dynamical systems. In particular, say, so two systems can only be equivalent if the underlying space on which they defined is a homeomorphic. So let's think, for example, of interval maps. If you have two maps of the interval, right? So we have now the world of all maps of the interval. And we have this equivalence relation that separates them into equivalence classes, right? So we've taken all the possible interval maps. So we have now, if I is an interval, okay, so topological conjugacy is an equivalence relation on all possible interval maps. So we want to explore a little bit what these equivalence classes look like, right? Because otherwise, what's the point? Okay, we've defined this concept, but now we want to use this to understand a little bit the space. Like this was the original objective. We want to have some kind of classification. So we want to know, okay, the same way in which you want to know all possible groups up to isomorphism, right? You want to classify them. Ideally, we want to know all possible interval maps, say, up to topological conjugacy, right? So if two maps are topologically conjugate, we bunch them all in the same class, we say they're the same, and then we want to know what possible kinds of topological conjugacy equivalence classes we have. So this is not easy. In fact, it's not essentially impossible to really know all of these, but we can go some way to understand some of these equivalence classes. And in particular, a very interesting question then is the following. Suppose you start with a map. Suppose this one, I just left it on here because it is one. We know that this is conjugate to the quadratic map that we had before. But now suppose that I just perturb this map a little bit, right? Suppose I change it a little bit. So I just, it's not piecewise affine anymore. I just change it like this. Then a natural question is, okay, how significant is this perturbation? How significant is this change? Right? And now that we have the notion of topological conjugacy, we can formalize this idea because, of course, the map we had before and the new map, they are different maps, right? And so we could use all kind of heuristic arguments to say, well, but it's almost the same because this one has just one fixed point, the other one has just one, has also one fixed point. So, but okay, I say, okay, but what happened to the periodic points, for example? You know, I said that we could show that if this map, piecewise affine full branch maps, they had the dense set of periodic points. What about this new map, right? Does this still have a dense set of periodic points? Or, you know, more formally now that we have this notion, is this new map topologically conjugate to the old map? This is the formal way, precise way to formulate mathematically the question: if you take a map and you perturb the map, what happens to the dynamics, right? And clearly the points will change, the dynamics will change, because this point will now map here instead of mapping here. But if I'm able to say, okay, the dynamics changes, but the new map after the perturbation is topologically conjugate to the old map, then in some sense not much has changed. It means that I've just changed a little bit the position, but the topological conjugacy still matches up all the periodic points, all the orbits, all the omega limits, and everything, right? So this is the problem, or this is the question of structural stability. So informally, we say that that a map is structurally stable if small perturbation, any small perturbation, if I just change it a little bit, then the new map is still topologically conjugate to the old one. This was a very important concept that was actually introduced in the early 1900s. And if you think about it, one of the motivations for dynamical systems, I think one of you asked me at the beginning of the course, you know, whether there's applications to these systems. And one of the dynamical systems are first and foremost motivated, maybe not first and foremost, it depends on your point of view, but they're also very much motivated by modeling phenomena, natural phenomena, which change. You know, all around us in the world, we have dynamical systems because things evolve according to certain law. They have orbits and they change, right? So dynamical systems are used to model real-life phenomena of all kinds that evolve in time. So when you take a real-life phenomena, what you're doing is you need to make a mathematical model. When you take you create a dynamical system, you're creating a model of that real-life phenomena, right? But you don't know that it will be exactly correct, that model. So you say, okay, a model is this map here. Maybe I made a mistake. Maybe the real-life dynamical systems is more closer to this map, okay? Or maybe something similar. And the question is, have I made a big mistake or a small mistake? If I use a model that is almost correct, does that completely invalidate my conclusions, or is the dynamics of this nearby model very similar? Okay, this is a fundamental question that can be tackled in many different ways and can give many different answers. But this is one way to think about it and to talk about it, right? Is to say, okay, if I know that a small difference is not going to change the topological conjugacy class, then I say, okay, it's a good enough model, right? Because in real life, you expect models to be kind of robust. You know, you don't expect models, dynamical phenomena, to behave in a way that a tiny difference can make a big change, although this takes us back to sensitive dependence on initial conditions, which we will come back to, right? This is about whether once you have the model, if you change the initial condition, what effect does that have? But more globally, is if you change the model, is the dynamical system the same or not, right? So this is formulated mathematically with this notion of structural stability. So to formulate precisely structural stability, I'm missing another notion, right? Because now I have defined topological conjugacy, or I can choose conjugacy or C1 conjugacy, but I've said that I want to make a small perturbation, right? So I need to define what I mean by a small perturbation. This map. So the philosophy of structural stability is that if G, let me write G, is a small perturbation of F, then F and G are topologically conjugate. This is not a theorem, this is a heuristic definition of what we mean by structural stability. Then we have to prove in various situations whether this is true or not. And in particular, we need to define what we mean by a small perturbation. So before we do that, let me give an example of a system that is clearly not structurally stable. Let's look at the world of interval diffeomorphism that we had before. Right? Suppose we have, if you remember, we showed that we can have some interval diffeomorphism where the fixed point here has derivative 1 and it's tangent the diagonal. So here we have a fixed point, it's tangent to the diagonal. So why would I say that I think this perhaps is not structurally stable, even though I've not defined the concept precisely, intuitively? How would you describe, how would you kind of convince yourself that a small perturbation of this is not necessarily in the same topological conjugacy class to this map? Anyone suggest what kind of perturbation we can make?
Make a perturbation near fixed point.
Near which fixed point?
The fixed point along the diagonal.
Near this fixed point. And what is the perturbation going to do?
Just make it a bit down.
Exactly. And what effect is that going to have?
We will have more fixed points.
Exactly. Right? So here we can have a map that is exactly the same, but here we change it a little bit. So that it now has two fixed points. Whatever little bit means, right? We've not defined, but it looks like a little bit, right? If we can even make it even smaller like this, right? And it can even be the same everywhere here. So this looks like just a small perturbation. Or we can also make a small perturbation where we eliminate the fixed point, right? If we make the perturbation like this. So we lift it a little bit here, then this will have no fixed point. What effect does this have on the global dynamics? This can have a big effect on the global dynamics, right? Because when you had this fixed point for the original map, so remember what is this point? So this point is attracting, now I didn't See, this picture is not very good. So this picture, this is, I should have drawn it a little bit more like this, sorry. Okay, so this fixed point is attracting on the left, and it is repelling on the right. Remember, this has this property, but certainly all the points between 0 and P, they converge to P. Now, if we change it a little bit and we get rid of the fixed point, then what's going to happen to this point here that for the original map was converging to P? What's going to happen to this x0 here? Now, this fixed point is going to go past and is going to converge to this point, to 1. So this is a big change in the dynamics. If you are this initial condition and you thought you were going to end up in P, and suddenly you end up way, way over there, right? So it's not just, so I'm trying to emphasize the fact that by deleting this fixed point, we've not just say, okay, we have one less fixed point, but the lack of this fixed point has a global effect on a lot of orbits, that all these orbits that were coming to here, suddenly they're going all the way there, right? They're going all the way to, so it changes the omega limit set of all these points significantly, okay? So this is a very good example of a map which is clearly not structurally stable. Or we would not want it to be defined as structurally stable in our definition of small perturbation, right? Okay, so we need to finish, so I just want in the last couple of minutes to define, so what we need to define small, all we need is a metric on the space of interval maps, on the space of dynamical systems, right? Because small is just a question of measuring the distance between these two maps, right? The small perturbation means that the map F and the map G are close in some kind of metric, okay? So we can define, if I is an interval, we define the so-called C0 metric between two interval maps. So suppose F and G are both maps defined on the same interval. And then the distance, the C0 distance, is simply equal to the maximum of f of x minus f of g for all x, y in I. So this means that you look at the graph of f and the graph of g, and for each point, you look at the value of f here, and you look at the value of g here, and you take the difference. So it's really, literally, the distance between the graphs, the maximum point on the distance between the graphs. And then we can also define the C1 metric between these 2 points, and this is equal to the maximum, maximum of fx minus, there should be a absolute value here, fx minus g of x, this is just x, for all x and y, right? F of x, g of x, and here you would put also the derivative, f of x minus g prime of x for all x in I. So this means that now you look at each point, you look at this point here, x, right? And you look at the distance between the graphs, and you plug it here. And then you look at the distance between the derivatives. This one has a certain derivative, this other one has a certain derivative. You look at how close the derivatives are, and you plug it in here, and you take the maximum of these. And then you can define in the same way the D2 distance between f and g equals the maximum between f of x minus g of x, f prime of x minus g prime of x, and f double prime of x minus g double prime of x, x in I. Okay, and again, and I'm almost finished here, so I will leave it as an exercise to check that these are metrics. These are very significant metrics that we're going to use a lot. They're metrics on the space of interval maps, okay? In this case, of course, in this case, it's enough for the maps to be continuous. In general, no, they don't even have to be continuous, but in general, we apply them to continuous maps, so at least they have to be defined on the same interval. Here, they need to be differentiable, and here they need to be twice differentiable for us to be able to define this, right? And this, I will give some exercise, and maybe we can talk about it a little bit more in the next lecture. But maybe I'll do that because I think it's important to understand the difference between. These are, as you can see, metrics that really give different, that not equivalent metrics. So you may have two maps which are very close in the C0 metric because this is small, right? But they're not close in the C1 metric because you may have this, this is the graph of one map, and you may have the other one that wiggles a lot, oscillates a lot here, right? So the distance between the two graphs is always small, so it is close in the C0 metric, but the C1 metric is big because there's some points here where the derivative is very different in the two, and even more in the C2 metric. So we need to specify now in structural stability, I will discuss this a little bit more later, we need to specify which of these metrics. So what do we mean by a small perturbation, right? So we say that something is structurally stable if there exists some epsilon such that all the maps which are epsilon close, if your perturbation is less than epsilon, then the new map will still be topologically conjugate. So you've not had any bifurcation. This is sometimes called a bifurcation when you change your topological conjugacy class. And then it makes a difference. So the map might be structurally stable in the sense that if you make a C2, small C2 perturbation, then you're guaranteed to remain in your topological conjugacy class. But if you make a small C1 perturbation, that gives you more flexibility. If you make a C0 perturbation, that gives you even more flexibility. So you can have many more maps that are C0 within epsilon, C0 epsilon, and not C1 epsilon, and so you can create more different phenomena, okay? So in this part of the course, what we're going to do is next time explore a little bit more this notion of structural stability and the different topologies you can have on your space. But most importantly, I want to give techniques for showing that maps are topological conjugacy and therefore structurally stable. And there are at least 4 very interesting techniques, but unfortunately we don't have time to do all 4 of them, so I'm going to do 2 in this course. And really the focus is on that, on the techniques that we're going to use to show which systems are topological conjugate to each other, which leads also to results about which maps are structurally stable or not. Okay. So thank you very much, and see you next time. Bye.